Okay, so at the previous lecture we discussed an important class of compact quantum groups, namely the compact matrix quantum groups. And we introduced our main example, namely the quantum SU2 group, which was originally introduced by Voronovich in 1987. Well, I also promised you to give some other examples of compact matrix groups, in particular the so-called free quantum groups. But well, if you don't mind, I'll just move this material to the exercise sheet, just to save time. So mostly these examples are essentially simple exercises. Okay, and so our main goal for today is to construct the Haar state on compact quantum groups. So this is a natural quantum analog of the Haar measure. But before we construct the Haar state, let's make a short digression into the C-star algebra theory, and let's discuss the so-called slice maps. Slice maps on minimal C-star tensor products. So we start with some notation. Suppose that H is a Hilbert space, and X and Y are two elements of H. So we introduce the following rank 1 operator, X circle Y. This is a bounded operator on H, which acts as follows. It takes an arbitrary element Z to the following vector. So this is a rank 1 operator, and its image is the one-dimensional subspace spanned by X. We have some useful formulas related to such operators. A proposition. First of all, if we take an arbitrary bounded operator T on H, then the product of T and this one-dimensional operator X circle Y is again the one-dimensional, the rank 1 operator corresponding to the vectors T, X, and Y. Similarly, if we multiply by T on the right, then we get the following: X T star Y. And finally, part 3, if we take two rank 1 operators, X, Y, an arbitrary operator T, and multiply T by these rank operators on both sides, say X, Y, and Z, W, then the result looks as follows. The inner product of T, Z, and Y multiplied by the rank 1 operator X, U. And also part 4, the norm of such a rank 1 operator, X circle Y, is just the product of the norms, the norm of X multiplied by the norm of Y. The proof is a simple exercise for you. This is very elementary. Okay, now we have the following theorem. Suppose that we have two C-star algebras, A and B. A and B are C-star algebras. And suppose that f is a bounded linear functional on A. I claim that there exists a bounded linear operator denoted like this. F tensor 1, which takes the spatial C-star product of A and B, C-star tensor product of A and B, to B. And this operator is uniquely determined by the following formula. It takes each elementary tensor, A tensor B, to f of A B. And this is a so-called slice map on the tensor product. So in some sense, it cuts off a slice from the tensor product and takes the tensor product to B. Well, if we replace here the minimal C-star tensor product by, for example, the algebraic tensor product, or by the projective tensor product of Banach spaces, then the result is absolutely trivial because of the universal properties of such tensor products. We just consider the respective bilinear map and linearize it. So we factorize it through the respective tensor product. But of course, this is not possible. It is not possible to do this in the setting of minimal C-star tensor products, for the simple reason that this tensor product is not given by universal property. So we must invent something different, a different argument. This result is, in fact, this is a classical result due to Takesaki. But the proof I'm going to tell you is not entirely standard. It's relatively new, and it is due to Pirkovskii. So we consider, first of all, the respective map on the algebraic tensor product. F tensor 1, which takes the algebraic tensor product of A and B to B, and it is uniquely determined by the following formula. Clearly, this map exists and is unique. Now, to prove the theorem, it suffices to show that this map, F tensor 1, is bounded with respect to the spatial tensor norm, and that the norm of this map is less than or equal to the norm of F. Oh, by the way, I forgot to tell you that, so let's write the respective statement in here. So moreover, the theorem states that the norm of this map, of the slice map, is equal to the norm of F. So if we show that the respective map on the algebraic tensor product is bounded and the norm of this map is less than or equal to the norm of F, then we are done, because then we can extend by continuity this map to the spatial C-star tensor product. So the same inequality holds. And the opposite inequality is clear because we can just evaluate this map on elementary tensors. So now we have to show that this map is bounded and that the norm of this map is less than or equal to the norm of f. So first of all, we do the following. We embed B into B of H, into the algebra of bounded operators on a suitable Hilbert space. This is possible by the second Gelfand-Nymark theorem. And let's look at the following picture. So this is our slice map, F tensor 1. So B is isometrically embedded into B of H. And we have a similar map on the algebraic tensor product of A and B of H, F tensor 1. And we have an inclusion here. And moreover, both the vertical arrows are isometries. So by assumption, this arrow is an isometry, and it follows from the basic properties of the spatial C-star tensor product that this arrow is also an isometry with respect to the minimal C-star tensor norms. So this picture shows that everything is reduced to the case where B is exactly B of H, because if we know that this map is bounded and its norm is less than or equal to the norm of F, then the same is true for this map, because the vertical arrows are isometries. So we may assume, so this picture implies that we may assume from the very beginning that B is the algebra of bounded operators on H. And for simplicity, let's denote our map by big F. So big F is little f tensor 1. Okay, so now we take an element U in the algebraic tensor product. Oh, before we do it, let's make one more simple observation. Namely, let's observe that our map big F has the following algebraic property. First of all, both B and A tensor B are B bimodules in a natural way. So B acts as just by multiplication on the left and on the right. And let's also observe that F is a morphism of B bimodules.
How does it act on the left?
On B or on the tensor product?
On the tensor product.
On the tensor product, well, we forget about A, so it acts on the right by multiplication on the right, and we just, well, maybe it's better just to write a formula. So B acts on A B prime as A B B prime. So A tensor B becomes a B bimodule. Okay, and yeah, is that clear? Vladislav?
Yeah.
Okay. So both B and the A tensor B are B bimodules, and let's also observe that F is a morphism of B bimodules. This follows from the explicit formula for F. Okay, so now we try to estimate the norm. To estimate the norm of f of u. So let little u be an element in the algebraic tensor product. So let's first of all observe that the norm of f of u, now f of u is a bounded operator on H. And this can be written as the following supremum. So we consider the following inner products where x and y run over the closed unit ball of H. And we have this equality. So this is simple exercise in functional analysis. This equality holds for each operator on the Hilbert space. Okay, so now we do the following. We take arbitrary elements x and y from the unit ball, and also an element little h. So x and y are in the unit ball, and little h is on the sphere. And let's consider the rank 1 projection, orthogonal projection P, which is just H circle H. So this is the rank 1 orthogonal projection, which projects everything on the linear span of H. So now we look at this number, which appears in this formula, and we multiply this number by P. So we get the following operator. So clearly the norm of this operator is just this, the absolute value of this number, because the norm of P is 1. And now we write this operator as the following triple product, H circle Y, f of u, and x tensor H. Well, this is a special case of our previous proposition. A special case of this formula, formula 3. Okay, now we recall that F is B by modular morphism, so we can take these two rank 1 operators and move them inside F. So this is F applied to H circle Y, U, X circle H. Okay, so now we look at this triple product, and we easily observe the following. This is a little elementary exercise to show that this element, this operator, well, this is not an operator because this is an element in the tensor product of A by B of H. And this element sits actually in the tensor product of A and the one-dimensional space spanned by P. Sits in A tensor CP. To prove this, you just substitute elementary tensor and an arbitrary elementary tensor for U and make a little calculation. So this exercise implies that this element can be written as the following simple tensor, B tensor P, for some element little b in our algebra A. Okay, now we can continue our calculation. We use this equality, and now we write the norm of f of u as follows. So the norm of f of u, well, not the norm of f of u, because the norm of f of u is the supremum. but the absolute value of this number, which appears in this formula, for u x inner product with y. So what is this? This is the norm of following operator, because the norm of p is 1. Now we use this equalities and this equality. So we substitute B tensor P here. So this is just big F applied to B tensor P. Okay, now, but what is big F? Big F is a little f tensor 1. So when we apply this to B tensor P, what we get is f of B P. And since the norm of P is 1, this is just the absolute value of f of B, which is less than or equal to the norm of f multiplied by the norm of B. Finally, we again replace B by B tensor P, because the norm of B tensor P is equal to the norm of B. And finally, we look here. We look at this equality, which implies that the norm of this element is less than or equal to the norm of U, just by the submultiplicativity of the operator norm. So this is less than or equal to the norm of F multiplied by the norm of U. And that's it. So we have this estimate. The right-hand side doesn't depend on x and y. And finally, we get the supremum of this over the unit ball. So x and y run over the unit ball. And as a result, we see that indeed big F is bounded. And the norm of big F is less than or equal to the norm of little f. And this is exactly what we wanted to show. So this completes the proof. Okay, so we constructed our slice maps. And from now on, we adopt the following simplified notation. Namely, we will suppress the star from the notation for the slice map, and we simply write f tensor 1 for our slice map. Usually, this doesn't lead to any confusion. As a corollary, we get the following result. Suppose that f is a bounded linear functional on A and g is a bounded linear functional on B. Then there exists a bounded linear functional f tensor g on their spatial C-star tensor product. Uniquely determined by the following formula. So it takes each elementary tensor A tensor B to f of A g of B. Well, the proof is immediate from our previous theorem. We simply define this functional as the following composition. And this is exactly what we want to construct. It takes A tends to B to f of A, g of B. Or equivalently, we can write also g applied to f tensor 1. This gives us the same map. Okay. By the way, it's interesting to remark that it's essential that we work with linear functionals here and not with arbitrary linear operators. Of course, again, if we replace the minimal tensor product by the algebraic tensor product or by the projective tensor product of Banach spaces, then we can perform a similar construction for linear operators. But this is not possible in the context of C-star algebras. So we have the following exercise. So let H be the little space, infinite dimensional separable Hilbert space. And let's consider the so-called transpose map, theta, on K of H. Which takes each operator T to T transpose, where T transpose is uniquely determined by the following formula. Here, EI is the standard orthonormal basis of the little L2 space. So in matrix form, theta is just the transpose operator. It takes each T to T transpose. So prove that theta is bounded. But if we consider the tensor product with the identity map, so this is a map which takes K of H, tensor K of H to itself. So this map is unbounded. With respect to the spatial C-star tensor norm. So this exercise shows that we cannot do the same construction. We cannot apply the same construction to linear operators. It can happen that the respective tensor product will be unbounded. Okay, so now we are ready to discuss the Haar state on compact quantum groups. Well, to begin with, let's start with the classical situation. Suppose that G is a locally compact topological group and suppose that mu is a positive Radon measure. On G. In general, mu is not necessarily finite. By definition, we say that mu is left invariant. And respectively right invariant. If for each Borel subset of our group, for each Borel subset B of G, and for each point little x in G, we have the following equality. So this is the left invariance property, and for the right invariance, we have the following. And well, of course, there's a trivial example, the measure which is identically 0. But if we require that b is not, if we require that mu is not identically 0, if mu is not identically 0, then we say that mu is a left Haar measure, or respectively a right Haar measure on G. The Haar measure is named after Alfred Haar, a Hungarian mathematician whose PhD supervisor was Hilbert. By the way, Haar is famous not only for the Haar measure, but also for the so-called Haar system, which is a special orthogonal system of functions, which is very important, in particular in applied mathematics. Well, we have some obvious examples of the Haar measure. For example, if G is discrete, then we can take just the counting measure. The counting measure is a measure which is defined on all sets, and it just it takes so mu of b is just the cardinality of b, which is either finite or infinite. Another obvious example is the Lebesgue measure. On the real line or on Rn, or for example on the torus. So these are the most obvious examples of the Haar measure. And we have the following fundamental result due to Haar, von Neumann, and Weil. First of all, this result states that there exist a left and a right Haar measures. On G. Second, a left Haar measure is unique in the following sense. If, say, mu and u are left Haar measures,
Excuse me, are you sure this is A Weil, not H Weil?
absolutely. Hermann Weil is also also made many important contributions to representation theory, and especially in the case of compact groups. But André Weil, who is most famous for his contributions in number theory, started his mathematical career with by proving several important results on in harmonic analysis. And in particular, he proved, well, I'll tell you more about the history of the theorem, but he obtained many interesting results in harmonic analysis. So this is not a mistake. This is indeed André Weil. You can easily find his important monograph, very little but interesting book, Integration on Topological Groups and its Applications. Of course, he was mostly interested in applications in number theory, but in fact, this book is not about number theory, but is about harmonic analysis. So the uniqueness of the Haar measure, if you have two left Haar measures on G, then there is a positive constant C such that the following formula holds. So in other words, the left Haar measure is unique up to a multiplicative constant. And of course, we have a similar result for right Haar measures. And finally, part 3, if G is a compact group, and mu is a positive random measure on G, then mu is left invariant if and only if it is right invariant. But for arbitrary locally compact groups, this is not the case. There are examples of locally compact groups for which the right Haar measure and the left Haar measure are different. So this result is essentially due to Haar, von Neumann, and Dale. So first of all, the existence of the left and right Haar measures was proved by Haar in 1933. In a special case where G is second countable. In 1934, von Neumann proved this both the existence and the uniqueness of the Haar measure in the case where G is compact. And the general case is due to under Dale. In the case where G is compact, it's customary to normalize the Haar measure in the following sense. If G is a compact group, and mu is a Haar measure, when we say that mu is normalized, if it is a probability measure, that is mu of G is 1. And it's immediate from the above theorem that such a measure is unique. Okay, so our goal will be to extend this notion to the case of compact quantum groups. So what is a reasonable analog of Haar measure in the case of compact quantum groups? So let's do the following. Let's look at the definition of a Haar measure and let's try to dualize it. That is to write the left invariance property in dual terms, in terms of the algebra of continuous functions on G. So suppose that, again, G is a compact group. G is a compact group. And suppose that mu is a positive Radon measure. We denote by H the respective functional on G, on C of G, sorry, which takes each function f to the integral of f with respect to mu. Also, we introduce some notation. So for each point x in G, we
integral by the whole group.
Of course, yeah. When I don't write explicitly the integration domain, I mean that we integrate over G. So now we introduce a special notation for the shifted measure. So for each x in G, we define a random measure Lx mu on G by the following formula. Lx mu is of B is mu of X inverse B. So now the definition of the of a left invariant measure means that mu is left invariant if and only if for each x in G mu of mu equals Lx mu. Well, two measures are equal if and only if their respective integrals are equal. So this means that for each f in C of G, the integral of f with respect to mu is equal to the integral of f with respect to Lx mu. Now the left-hand side of this equality is just h of f, and we can write the right-hand side as follows. It's a simple exercise to show that this is the integral of f of xy d mu of y. And now we call that C of G is C star by algebra. So the co-multiplication delta is given, it takes f to the function f of xy. So what is this? This expression is nothing but the slice map 1 tensor f applied to delta f. Not to delta f, and 1 tensor h, of course, not f. H is our functional. 1 tensor h applied to delta f. Okay, so to make this formula more compact, let's introduce some more notation. Which makes sense for an arbitrary unital algebra. So if A is a unital algebra, then we denote by a little eta the unit map, that is the unique linear map from the complex plane to A, which takes the identity to the identity. So by using this notation, we see that mu is left invariant if and only if the following identity holds. 1 tensor h delta equals eta h. And similarly, we obtain that mu is right invariant if and only if h tensor 1 composed with delta equals eta h. So this is the dual formula for the left respectively right invariance property of a positive Radon measure. And we can simply extend, we can take these identities and we can use them as definitions of left and right invariant states on a compact quantum group. So we give the following definition. Suppose that A with comultiplication delta is a compact quantum group, and suppose that H is a positive linear functional on A. We say that H is left invariant if the following formula holds. And similarly, we say that H is right invariant if we have the following identity. Okay. Now, these invariance properties can be conveniently written in terms of the convolution on the dual space of A. So we give one more definition. We define the convolution of two linear functionals, f and g, to be the linear functional f star g. This is linear functional again on A, defined by the following formula. So we take the commultiplication and compose it with f tensor g. And the result is a linear functional on the tensor product, on A. So we get an operation on the dual of A. By the way, an important special case, so let's come back to the classical situation for a moment. An important special case is the convolutional of measures. If G is a compact group, and if mu and nu are complex random measures on G, then their convolution is defined by the previous formula, and explicitly it can be defined as follows: for each continuous function f, the integral of f with respect to this measure is the integral of f of xy, d mu of x, d nu of y. For an arbitrary continuous function f on G. Okay, now again we assume that A is an arbitrary compact quantum group. So we have the following simple exercise. First of all, if we equip the dual space with the convolution multiplication, then we get a Banach algebra. In fact, the associativity of the convolution is immediate from the co-associativity of the co-product on A. Second, it's easy to show that if we take two positive functionals, f and g on A, then their tensor product, f tensor g, is also positive. And this easily implies that the convolution is positive. And we have a similar result for states. If f and g are states, then their tensor product is a state. And this implies that the convolution is a state. Okay, now we have the following useful criterion for the left invariance or the right invariance in terms of convolutions. So as before, we suppose that A is a compact quantum group and H is a state. Well, actually not necessarily a state, just a positive linear functional on A. Then the following conditions are equivalent. Condition 1, H is left invariant, respectively right invariant. Condition 2, for each linear functional omega on A, the convolution of omega and H equals omega 1 multiplied by H. This is the left invariance, and for the right invariance, we have H convolved with omega is omega of 1H. And part 3, for each positive linear functional, we have the above property 2. In other words, it's enough to check property 2 for positive functionals only. Okay, let's prove the equivalence of these conditions. So what is the convolution of omega and H? So by assumption, this is omega tensor H composed with delta, or equivalently omega composed with 1 tensor H composed with delta. So this gives us the left-hand side of this equality. And similarly to the right-hand side, omega of 1H can be written as follows. This is omega eta H. So these equalities obviously imply that 1 implies 2. Hence, 1 implies 2. So we just take the definition of a left invariant functional. So this is the definition, and apply omega on the left. Okay, now clearly 2 implies 3. This is clear. And to complete the proof, we need the following lemma, which is an exercise for you. The lemma states that states of A separate the points. So for each non-zero element A, this holds for actually for an arbitrary C-star algebra. For each C-star algebra A, and for each non-zero element little a, there is a state omega on A state such that omega A is not 0. So a hint is to use the fact that this is true for normal elements. So some time ago we proved, before we proved the second Grafan-Dynamic theorem, we proved that for each non-zero normal element A, there is a state such that omega A is non-zero. So to extend this to an arbitrary non-zero element, you just take the real and the complex parts of A. A equals B plus IC, where B and C are self-adjoint. Okay, now to complete the proof, we have to show that 3 implies 1, or equivalently 3 implies 2. Well, it's really more convenient to prove that 3 implies 1. So formula 3 means that omega applied to 1 tensor h delta minus eta h is 0 for each state. This is an equivalent form of condition 3. But now we apply our lemma, which shows that if this holds for each state, then this expression here is identically 0. So H is left invariant. So this completes the proof. So actually, we considered only the case of left invariant states, of left invariant functionals, but of course the right-hand side is the right-hand version is similar. Oh, okay. Okay, now we are ready to construct her state on an arbitrary compact quantum group. So we have the following theorem due to Voronovich. Suppose that A is a compact quantum group. Part 1, there is a state H on A such that H is both left invariant and right invariant. And part 2, such a state is unique in the following strong form. If F is another state on A, such that F is either left invariant or right invariant, then F equals H. And this state H is called the Haar state. The terminology is clear because in the case where A is commutative, we know that A is the algebra of continuous functions on a compact group. And in this case, H is just the integration with respect to the Haar measure. It will be convenient to divide the proof into 3 steps. So step 1, or lemma 1, for each state omega on A, there is another state H such that the convolution of omega and H in any order gives us H. So essentially, we have the same formula as in the definition of left invariant state, but the problem here is that H depends on omega. So this is some weak form of the existence of a left invariant state. To prove this result, we consider the following sequence of states. So let Hn denote the following arithmetic mean: 1 over n, omega plus omega convolved with omega plus, and so on. So the last functional here will be the nth power of omega with respect to the convolution product. So clearly this is a state. This is a state on A. Why is it a state, by the way? Let's recall that in the unital case, and here A is unital, in the unital case, a state can be equivalently defined as a positive functional, which takes the identity to the identity. So clearly this takes the identity to the identity, and so it's a state. So we have a sequence of states, and now apply the Banach-Haloglu-Bouraki theorem, which implies that the set of states equipped with the weak star topology is compact. Well, indeed, it's a closed, weakly star closed subset of the unit bubble, which is weakly star compact. So we can, since it is compact, we can find a convergent subnet. There is a subnet of the sequence Hn of lambda, which converges to a state little h. So I claim that little h is exactly what we are looking for. Well, indeed, if we convolve omega and Hn, and consider omega Hn minus Hn, so equivalently we can convolve on the opposite side, and a little computation shows that this will be 1 over n, and when we take the difference, only two functionals survive, namely omega to the power n plus 1 minus omega, and other terms cancel. Okay, but this expression in brackets is bound because the norm of each state is 1, and 1 over n goes to 0. So when we take the limit over the respective subnet, we conclude that omega h minus h equals h omega minus h equals 0. And this completes the proof of lemma 1. Okay, now lemma 2, which is actually the key point in our theorem, the key technical point, lemma 2. Suppose that H is a state on A, and suppose that omega and nu are two positive functionals on A, satisfying the following inequality. So this inequality means that both omega and nu are positive, and moreover that omega minus nu is also positive. I claim that if we have the following identity, omega h equals h omega equals omega of 1h, then we have a similar formula for nu. Nu h equals h nu equals nu of 1h. Well, the proof of this lemma is a little bit technical. So before we prove lemma 2, let's show how these two lemmas help us to complete the proof of the theorem. Proof of theorem modulo lemma 2. So we do the following trick. For each positive linear functional omega on A, we introduce the following set that's denoted by k omega. This is the set of those states H on A for which the following formula holds. So what we are going to do is to construct a state H which satisfies these relations for each omega. So what can I say? What can I say about k omega? Well, k omega is well. First of all, a little exercise. The convolution on a star is separately weakly star continuous. This easily follows from the definition of the convolution. So it is separately weakly star continuous, and this implies that k omega is closed, is weakly star closed. So it is compact. So it is compact. Now let's observe that if we take a finite intersection of such sets, say k omega 1 to k omega n, then this intersection contains k corresponding to their sum, omega 1 plus up to omega n. Why is it so? This follows from lemma 2. Well, indeed, if say nu is the sum, if we denote by nu this, by a little nu this sum, this is a positive functional. Sorry, not nu, but just omega, then of course omega dominates each omega I, and if we apply this lemma to omega I and omega, then we see that if this formula holds for omega, that is for the sum of omega 1 up to omega n, then the same formula holds for each omega I. In other words, if a state H sits in here, then it sits in each set from this intersection. So we have this inclusion. Okay, let's now apply lemma 1. So lemma 1, each set k omega is non-empty. So let's look once again at lemma 1. So for each omega, there is a for each omega there is a state little h such that this property holds. Well, formally we prove this only in a case where omega is a state, but if omega is an arbitrary positive functional, we just normalize it. We divide omega by omega of 1, and we get a state. So of course, everything is used to the case where omega is a state. So we see that what we've just constructed, namely the family of sets k omega, this family of compact sets with the so-called finite intersection property. So any finite intersection is non-empty. And a standard result from general topology implies that the intersection of all these sets is non-empty. Over all positive functionals omega. So to complete the proof, we just take any element from this intersection. In fact, we will see soon that it is unique. And observe that just by the definition of k omega, H is both left and right invariant. Okay, so the final step is to show that H is unique, but this is just one line. Namely, if we have a state f on A, and if we assume that f is left invariant, then by the left invariance of f, we have the following equality. But we already know that H is right invariant, and the right invariance of H gives us that this is equal to H. And so f equals H. And of course, the same argument shows that if f is right invariant, then again f equals H. So this completes the proof of our theorem, modulo Lemma Two. Okay, now I see that we have only 4 minutes left, and this is not enough for me to prove Lemma Two. So let's postpone the proof of Lemma Two until the next lecture. So at the next lecture, we first prove Lemma Two, and then discuss some general results about co-representations of compact quantum groups. And that's all for today. Thank you.
Спасибо.